Good morning, class. Welcome to the online classes for physics of class 10th. In the previous classes, we were learning about the chapter light, in which we have gone through the topics that what are the mirrors, what are the types of mirrors. We have seen the mirror formula, we have seen the sign conventions for the two types of the mirrors, and we have seen the rules for the image formations also. And in the last session, we have seen that what was lens also. We have seen the introduction to lenses. So we have seen that what is lens, and lens is a piece of transparent glass but bounded by a two spherical surface. Whereas we have seen that mirrors are the part of a hollow sphere, right? It is a part of a hollow spherical glass. So it will have only one bent in surface or a bulged out surface which will having only one reflecting surface. But here lens is a piece of transparent glass which is bounded by two spherical surfaces. So here we can say that the two parts or the out surfaces are the reflecting surface. So we have seen that there are the two types of lenses, in which the first one was convex lens and the second one is concave lens. So what was the convex lens? Here you can see in the figure also, the figure A is the convex lens and the figure B is concave lens. So in the convex lens we can see that these lenses are thinner at the end and thicker at the edge. So we can say it's thicker at the middle. So what we can say that the lens is just thinner at the ends. You can see at the ends of the M and N they are very much thinner and thicker at the between. So these are the type of the convex lens, which are center it is thick but thinner at the edges. So we can say that here are the two surfaces from M and N. They both are bulged out surface from the center point. They are bulged out, and these bulged out two surfaces are the reflecting one. And the second one, that is the concave lens, which you can see in the figure number B. So here we can see that the concave lens are thicker at the edges, because here see the edges in the M and N in the figure A was thinner, whereas in the figure B the edges are thicker. So thicker at the edges but thin in the middle. So in the middle, at that is at the center, it is at thin, and whereas in the concave it is thinner, but in the convex it is thicker at the center and thinner at the edges. Okay, so this was the difference, that how you will get through the image itself that it is a concave or the convex lens. And now we will see that always a lens have the two spherical surfaces that may be bulged out or in the bulged in. So one is the concave lens and the other one is convex lens. So concave lenses, we know that they used to diverge the light rays. So the concave lens will be said as the diverging lens, whereas the convex lens converges the light ray. So they will be known as the converging lens. So you can see here that this is the converging one, that is the B, it is the diverging one. Because converge means whatever the parallel light rays or the beam of the light passing through the lenses will try to meet at a single point, and they will together come to the point, and this point is said to be the focus, right? Because whatever the light rays after the reflection meet at a point, that point is said to be focus. But whereas if you see in the concave lens, then what the light rays are doing, they are just moving out from the direction, that is moving out of the reflection, lights are moving out of the direction from the lens's bulged out surface. Okay, so from getting after outwards, that in the bent in surface, they are diverging to the other direction. So what we used to do, we just extend the light rays in the back direction and we find out the point where they meet after the reflection, and this point is said to be the focus. So this is what the lens was. That one is concave and the other one is convex. Convex are said to be the converging lens, whereas the convex is said to be converging and the concave is said to be the diverging lens. Okay. So next we have seen that in the mirror there was focus, focal length, center, radius of curvature, which are the parameters for the mirror. Right. Here also there are some parameters of the lens also. So here we can say that the lenses have principal focus, And we can say that for the mirror, the parallel beam of the light rays passes to one another, and after refraction, here the refraction will take place. We already discussed in the last class also that reflection took place where the reflecting surface is plane, that is in the spherical mirror or in the plane mirror. But here it will move through the thicker ends and the thinner edges, or at the thicker ends and the thinner edge. So we can say that the light ray is passing through the two mediums. So the light ray will go through the refraction. So the refraction will be done. So all the rays passing out through the lenses will maybe converge or will be diverged at some point F on the other side. It may be in the right or maybe in the left. So the point where these light rays after reflection or refraction meet are said to be the principal focus, which we have seen in the mirror also. So here in the lenses there will be two focus. Okay. So what we can say that if F is the principal focus for the light rays coming from the left side and the incident rays are also from the right side. So what we can say that they will converge at the other point. So one of the lenses will have the two focus. So there will be two focus for the lens, whereas in the mirror it was only one focus. So what this focus, second focus, the distances from the optical center, one on the either side of the lenses, we know that the distance from the focus to the pole of the mirror or the pole of the lens was said to be the focal length. So here there will be two focal lengths also, that is one will be given by small f and the other will be given by f dash. So but we have to see that the focal length of lens depends on the refractive index, right? Because it depends on the refractive index because the refraction is being done in the lens. So now we will see the rules for the light ray passing or the rules for the obtaining the images of the lenses. Firstly, we will be seeing the convex lens, and we will be thinking about the concave lens. And we know that whenever the light rays, that is the beam of light passing through the mirror or the lens, when these light rays are parallel to the principal axis, then they will refract through the lens, but after refraction they will passes through the focus. This was the first law which we have already seen in the mirror also. It will be similar to that in the convex or the concave lens also. So they will pass through the point focus F. And if the light rays in reciprocal to it was that when the light rays passes through the focus, then the refracted ray will be parallel to the principal axis. And we have seen the third one, that whenever the light ray passes through the center of curvature, then it will get reflect back, right? And here in the mirror we have seen the other rule also, that whenever the light ray incident on the pole of the mirror, then it reflect back with the same angle. But here, so this rule is not taken because the pole is not there for the convex lens. Now for the different image formation in the convex lens, you can see this table also, that whenever the object is kept at some infinity point, then we get the position of the image to be at focus second one, that is the second focus we will get the image, and the image will be of highly dimensioned and pointed size. Okay, so we can say that the image formed by the convex lens will be of real and inverted. Similarly, if we keep this object beyond the 2f1, that is the first focus, if we find that it is at the, because we are having the two focus in the either sides of the lenses, so here it will be f and the 2f will be there on the right side, and for the left side there will be f dash and 2f dash will be there. So if we keep this object beyond the 2f dash, then we get the image between f2 and the 2f2. So this is what the image formation will be, and the image size will be dimensioned, and the image nature will be real and inverted. Similarly, if we keep the object at the first focus itself, then what we will get, that the image will be of the same size and will be real and inverted, because no, that we have, if we keep an object at a focus, then we get just in the opposite direction at the downwards the image will be, and that will be the real and the inverted image. Now if we keep the object between the F and the optical center O, then we get on the same side of the lens as the object was. So we can say that it is a virtual and the erect because it is kept in the same size and in the same direction itself. We are getting in the same direction. So what we can say that the image formation in this situation will be virtual and the erect one. Okay. So if it is kept at between F and the lens O, then the image virtual and the erect, and either any of the topics if we kept anywhere in the object, then the convex lens will give the real and the inverted image. So convex lens, what is used? It is used as in the spectacles to correct the defect of the vision for the long sightedness. Mainly it is used for the long sightedness because it will be converging the light. Similarly, we have seen that the convex lens is used for making simple camera. It will be used in the magnifying glass. It will be used in the microscopes, telescopes. So the lenses are used in the microscopes mainly because we used to see that the images were very much dimensioned, or we can say that it will get a very highly magnified images. So we use the lenses over here. Okay. So we will be seeing now the concave lens. Now what the concave lens was? It is the image or a lens in which the bulged in surface is at the edges, that is thicker at the edges and thinner at the center. So here also the rules will be same, that whenever the light ray is parallel to the principal axis, then it will be passed through the focus. And similarly, after the reflection, that is if the light ray incident through the focus, then it will pass parallel to the principal axis, that reciprocal to each other. And similarly, if the light ray passes through the center of curvature, then it will move back in the same direction after the refraction. Okay. So here we will be seeing the formation of the images by the concave lens. So if the object is kept at infinity, then we will get the image at focus. And if we keep the object at focus, then we will get the image in infinity. And we get a highly damaged image by the concave lens. So remember that convex lens can give the real and the inverted image. But the concave lens always gives a virtual and the erect image. So what does it mean? That the focal length for the concave lens will be positive, but for the focal length of the convex lens will be negative. So if we kept it in between the optical center and the infinity, then also we will get the image as diamonds and will be a virtual and the erect image. Okay. So these are the ray diagrams that how we will be. You can see in the first one that the light ray passing parallel to the principal axis will be passing through the focus. So one is for the convex and the other one is for concave. So similarly, the second one, that when the light ray passes through the focus, then after reflection the light ray will be parallel to the principal axis. And if it passes or the point light ray is incident at the optical center, then it will get back or pass back with the same angle. Okay. So image formation also seen, and here the ray diagrams are here that see in the convex and the concave lenses, that when the object is kept at some 2f1, then we just get at 2f1 itself, but it will be in the downward direction, that is real, and the inverted image we will get. And if the light ray is passing through the parallel, that will converge at the point focus. If the object is kept beyond 2f1, then we will get at the point between f1 and 2f1. And the D diagram also you can see that whenever the object is kept between f1 and 2f1, then the image will be at beyond the 2f2, right? And if the object is kept at focus, it will get the image in infinity, and if the object is kept at infinity, we get the image at focus. Okay. So for the sign conventions, we know that if the object is kept with the direction of the incident line, then it is taken as positive, and if the image or we see the object at the different to the direction that of the incident line, then it will be taken as negative. Or we can say that the left side will be taken as the negative and the right side will be taken as the positive direction. So similar to that, we have seen for the mirror formula, we will be seeing that for the lens formula. So what is the lens formula? Is that normal difference between that to the lens and the mirror is that for mirror we have seen that it was 1 by v plus 1 by u as equals to that of 1 by f, where v and u gives the gives the distance of the object and the distance of the image. U is the distance of object and v is the distance of image, where f is the focal length. So in the mirror formula, we have seen that the formula gives us a relationship between the VU and F, which was given by 1 by V plus 1 by U equals to 1 by F. Similarly, for the length formula, it will be 1 by V minus 1 by U equals to 1 by F. So here also U will be the object distance, V will be image distance, and F will be the focal length. So this is the length formula, which can be expressed in the way of 1 by V minus 1 by U equals to 1 by F. So similarly here also the image distance, object distance will be taken negative for that of the convex, and for the concave the F will be positive. Similarly we have to take the sign conventions also. And the next thing, we have seen that magnification, that how the image formed will be of the height and how much the height is changed. This is said to be the magnification, which is equal to the height of the image upon height of the object, that is h2 upon h1. And similarly we can say that V by U is also given for the magnification. So let's see an example that the concave lens has focal length of 15 cm. So F is given as 15 cm. At what distance should the object from the lens, means what distance the object should place. So what we can say, that the U we have to find out, be placed so that it forms an image at 10 cm from the lens. So image distance is given, that is V is given as 1 by 10. So on putting these values, we know that the lens is a concave. So for the concave lens, we will be taking the U and the V value, and the F's value will be as negative, because in the concave the image formation will be of negative sign. So here you can see that for U will be taken as minus 10, for F it is taken as minus 15, and we have to find out the value for U. On calculating here, we get that U will be equals to that of minus 30 cm. So object distance should be kept at 30 cm to the left side. So what is the magnification? We already get the V and U, so we will find the magnification by V by U, that is 10 by 30. So it will be 1 by 3, which is equals to 0.33. So what this positive sign shows us, that the image is virtual and erect, and here you can see that magnification is 1 by 3. So the image size will be that of 1/3 of the size of the object. And see the next question, for the focal length of the convex. For the convex lens, we will be taking the focal length as positive. Object is always kept at the left direction itself, so we will be taking the value of U as negative itself. And for the image distance, we have to find it out. And the image will be positive because the image formation will be the right of the mirror. So height of the object is given as 2 cm. For focal length, F is given as 15, so which will be taken as a the focal length is taken as 10, which is given as a 10 cm, and the object is kept at the left side, which is taken as minus 15 cm. And to find out, we are to find out the U, V, because U is given here, so we have to find out the image distance as well as the magnification, that is how much the magnification is there. So 1 by V minus 1 by U equals to 1 by F, that is using the lens formula. We will be just applying the values of F and U, where the F is taken as positive for the convex lens. So it will be 1 by 30, or just taken as plus 30. So what does it mean? That the image is formed at a distance 30 cm and the image is real and inverted. So the magnification, how we will finding h2 upon h1. So we don't have the value of h or v. But yeah, we know that the magnification is also equals to v by u. So we can take this both equation, then it will be h2 by h1, which will be equals to v by u. So on taking these values, we get the magnification as minus 2. So what that means, that the image is real and inverted, and the formation of the image will be on the other side of the lens. So the image is 2 times enlarged because it is doubled. So now we will be seeing what the power of lens is. So what is power of lens? To find out the power of lens, we use the one formula also, as well as we have to see what is the power of lens. It is the measure that how much the light rays are converged or the diverged. So we can say that the power of lens is a measurement of the degree of the convergence and the divergence. So concave lens which diverges the parallelogram more strongly is said to have a greater diverging power. Whereas for the concave lens, it is said that the light rays are diverging, so it will have the greater converging power. So the power of lens depend on its focal length. So how can we define the power of lens? That the power of lens can be defined as the reciprocal to its focal length. That is what the light rays are meeting at a point focus, which how much it is distant from the optical center or from the lens. So it is given as power is equals to inversely proportional to that of the focal length, that is P is equals to 1 by F. So the inversely proportional to the focal length, that is if the focal length is short then the power will be more, and that if the focal length is long then the power of the lens will be less. Here we will be seeing that the unit of the power of the lens is given by diopter, that is D, and the power of the lens can be measured by an instrument named as dioptrometer, and the power of the convex lens is positive if the focal length is positive. And for what we used to take the focal length positive? For convex lens. So the power of lens for the convex lens will be positive, whereas for the concave lens we are taking F as negative, the focal length is negative, so the power of lens will be also negative. So therefore it is said to be the converging and the diverging lens. So the converging lens power will be taken as positive and the diverging lens power will be taken as negative. So this is about the topics which we have learned and the whole chapter. This is the last topic for your light, and the other chapter we will be starting in the next session, that is human eye and the colorful world. Okay, so we have seen that what is light. We have seen that the light travels in a straight line, tends to travel in a straight line, it does not need a medium. We have seen that the light rays parallel or incident on any surface, if it gets bounced back then it is said to be reflection. If the light ray passes from one medium to other medium, that is denser to rarer, then there is some changes, that is towards the normal or the away from the normal. This bending of the light ray is said to be the refraction. And we have seen plane mirror and the spherical mirror. In this mirror we have seen that the light rays phenomena is done by the reflection, whereas in the refraction it takes place in the lenses. And we have seen mirror formula and the lens formula, that is 1 by V plus 1 by U is equals to 1 by F, which was for mirror formula, and for the lens formula we have taken 1 by V minus 1 by U equals to 1 by F, where the different parameters were there, that is focal length, focus, pole, radius of curvature, aperture, height, image distance, object distance, focal length, and there were many more. So by seeing these parameters we also have seen the rules for the image formation of different lenses. But the rule for the parallel light rays moving, it will be same, that is if the light rays are parallel to that of the principal axis, then after reflection or refraction the light rays will be passing through focus. And if the light ray is incident to the focus point, the light ray after reflection or refraction will get parallel to the principal axis. Similarly, we have seen that if the light ray passes through the center of curvature, then it get back with the same direction. So this is what we have seen in the light chapter. So in the next session, we will most probably in this week itself, we will be starting this human eye and the colorful world. Okay, so thank you class.